this video, we'll be reviewing biconditional statements. A biconditional statement can exist when a conditional statement and its converse are both true, letting you write them as a single biconditional statement. A biconditional statement is a statement that contains the phrase if and only if, or the double-sided arrow. A counterexample is a false example to show that a conjecture is not true. So we're going to apply these definitions to try to create biconditional statements using a given statement. So in number 1, they give us the statement, perpendicular lines intersect to form right angles. So we want to change this into a conditional statement. Remember that a conditional statement is an if-then statement, and so we would write this as if lines are perpendicular, then they intersect at right angles. So we're changing it to an if-then. When we see two lines that are perpendicular, we see that they intersect at these right angles, so we know that that is a true statement. The converse of this is just to flip-flop the hypothesis and the conclusion. So we would write, if two lines intersect at right angles, then they are perpendicular. So we're just taking the conclusion and putting it up front, and then putting the hypothesis at the end to write the converse. Well, if there's two lines that are intersecting at right angles, then that does satisfy the definition of perpendicular lines, so that would also be true. So because we have the conditional and the converse both being true statements, we're allowed to rewrite this as a biconditional statement. And to do that, we end up getting the statement that says two lines are perpendicular if and only if they intersect at right angles. This can only be true if the lines intersect at right angles. If that doesn't happen, then there's no way we could ever call those two lines perpendicular. So because both of these were true, we were allowed to write the biconditional statement like this using the if and only if phrase there. We could also write this as P and then the double-sided arrow and then Q. So P is true if and only if Q is also true. So they're kind of like going back and forth there where they have to both exist and be true for this to happen. So if you want to try the next one, the statement that's given is that odd numbers are divisible by 3. So first change it to a conditional, see if it's true, converse, see if it's true. If they're both true, write a biconditional statement. If they're not, provide a counterexample. So you can pause the video and press play when you're ready to review. So here is what we can get in order to change this to conditional and a converse. So the conditional statement for this would be if a number is divisible by 3, then it is odd. So because we said that odd numbers are divisible by 3, then we're saying that that it would be odd. So this is false because 30 is divisible by 3, and that's an even number. The converse would be if a number is odd, then it is divisible by 3. So again, this would be false because I can prove 37 is odd, but it's not divisible by 3. So not only was my conditional statement false, but my converse was also false. So the biconditional is not something that we can write here because we didn't have a true conditional statement or a true converse. So even though this may be true sometimes, overall it's a false statement because we have counterexamples right here that are telling us, no, that's not always true, and here's why. This is when it happens. It's not true. We're going to now look at different types of Venn diagrams. So a Venn diagram is also called a set diagram, and it shows all the possible logical relations between a finite collection of sets. So finite means it's a limited amount of things, so we're keeping them contained in their different sets. Venn diagrams can be used to represent relationships and conditional statements. So a Venn diagram that's showing something is always part of another set would be if you play the cello, then you play in the orchestra. So if you're playing the cello, then you would also be playing in the orchestra. So the cello circle is within the orchestra circle because cellists play in an orchestra. In the sometimes column, we have heated seats and power windows, and those circles are overlapping in the middle, which would mean that there are heated seats and power windows in that overlap. So we would say the example there is that some cars have heated seats and some cars have power windows, but sometimes there's cars that have both, and that would be that overlap in the middle there. We can also have Venn diagrams that show things never intersect here. So a 5-sided shape and a square. If a shape has 5 sides, then it is not a square. We know that a square only has 4 sides, so a 5-sided shape would never overlap with a square, so their circles in the Venn diagram are separated. So I want you to try to pause the video and try these 4 problems below. Press play when you're ready to review. All right, well, hopefully you were able to give these a try. In the first example, it says, if you root for the Nationals, then you do not root for the Orioles. So we're saying that these are never going to overlap. So we're going to put them in 2 separate circles and say Nats fans are over here, Orioles fans are over here. These are not overlapping. You're not rooting for 2 different teams. You're only rooting for the one. In number 2, it says, if you are a student in a class right now, then you might understand Venn diagrams. So I'm going to draw a circle of students in the class. And I'm also going to draw a circle of understanding Venn diagrams. So I'm just going to label that as Venn diagrams. And because it said you might understand it, then you could be a student over here. You could be just someone that understands Venn diagrams, but you could also just be a student that understands Venn diagrams. So these overlap sometimes. Not everyone in the class may understand it, and everybody that understands Venn diagrams might not be in our class. So this is the section of overlap that said you might understand them. In number 3, they gave us the Venn diagram, and it said people who like snowboarding and people who like skiing. So this section of overlap kind of tells us that this is sometimes true. So we could say, if you like to snowboard, then you might like to ski. So not everyone that likes to ski likes to snowboard, and not everybody that likes to snowboard likes to ski, but there are people that do like to do both, and there are also people that don't like to do either, and they would be outside within this whole box. In the last one, they gave us this Venn diagram with the geometry students included in the math students. So the statement says, if you take geometry, then you are a math student. So because you're in a geometry class, that means you are a student who's taking some sort of math. And so because the geometry circle is within the math circle, then we can say that this is the true statement here.